And what happens when an observed rate law is inconsistent with the mechanism that you proposed? Well, you propose a new mechanism. So next is a slightly more complicated example, but as complicated as an example you will see in this class, and it's a different reaction. So let's give you the overall reaction first. It is the reaction of molecular bromine, Br2, with nitrogen monoxide to form NOBr. And let's say someone proposed, I've got a two-step mechanism here. I could have nitrogen monoxide colliding and reacting with a bromine molecule to form this NOBr2 thing. And I'm going to make it just a little more complicated. I'm going to suppose that this actually is an equilibrium. This reaction could go in the forward and the reverse direction. Now, when that's the case, we draw an arrow like that, and there is an explicit rate constant for both processes, or a separate rate constant for both processes. And I'm going to call it K1 for the forward direction and K-1 for the reverse direction. And I'm going to propose that the second step is that the NOBr2 collide with a second NO to form two of these NOBRs. And that one I'm going to propose is not really an equilibrium step, it just goes in the forward direction. And I will call the rate constant associated with that step K2. And I'm going to further suppose that the first step is the fast one, and the second step is the slow one. So the second step is the rate determining step, which means that we could propose a rate law that is equal to the concentration of NOBr2 to the first power times the concentration of NO to the first power, since the coefficient of both of these is 1 in this equation. But there's a problem with that, and that contains an intermediate species, namely the NOBr2. And it is considered, so step 2 is going to be the rate determining step. But the issue is that it is considered bad form to have an intermediate species in a rate law, because that's something whose concentration you can't control. So you could manipulate that to manipulate the reaction rate. So what do we do in that case? Well, let's look at the next slide. All right, so when cases like that, it's important to look at the step before it in the mechanism. And in this case, it's an equilibrium step. And this is something we can use to our advantage. So here's how we do that. So the idea is that the thought, or the hope, and this usually works out, is that for intermediates, they're normally going to reach some very small concentration. But after a very, very short buildup period, the concentration actually remains pretty small and constant. And that's going to happen when the rates of the two reactions, the forward and the reverse reaction, equal out. So mathematically, if the rates are equal, we can say this, that the rate of the first step is equal to the rate constant of the forward direction times the concentration of NO to the first power times the concentration of bromine to the second power. The rate for the second step, or the reverse step, is equal to the rate constant K-1 times NOBr2. And again, just to be clear, these rate constants, K1 and K-1, aren't necessarily opposites of each other. They are just different numbers. And the -1 here just implies that it's the reverse of step 1. But these two, if this really is an equilibrium step, these rates are exactly the same. And the idea is that you hope that you can express the concentration of your intermediate in terms of rate constants and concentrations of things that are not intermediates, actual legit products or reactants. And so if we rearrange this expression to solve for the concentration of NOBr2, we get this. It's equal to the quotient K1 over K-1 times the concentration of NO to the first power times the concentration of Br to the first power. So now we've got the concentration of NOBr2 expressed in terms of actual products or reactants. And then all you need to do is substitute this expression into, substitute this expression right here into wherever you saw the NOBr2 concentration expression in your proposed overall reaction rate, and what you want to do right here. So we propose that the rate, because this was the stolen, would be equal to K2 times the concentration of NOBr2 times the concentration of NO both to the first power. And now we have just substituted this expression there, and that gives us this monstrosity of K2, K1 divided by K negative 1 times the concentration of NO2 squared times the concentration of Br2 to the first power. And so the observed rate constant, K observed, is going to be equal to K2 times K1 divided by K negative 1. And you would expect this mechanism would result in a process that is second order with respect to NO, first order with respect to Br2, and third order overall. And again, you would do the experiment. If you observe this behavior, that was a good sign. If you did not observe this behavior, you come up with a different mechanism. All right, so this is an example that I often don't get to do in class, but I thought since we've got time, or the video can do whatever time it wants, we can do it. All right, so the overall reaction here is the reaction of molecular chlorine, Cl2, with trichloromethane to form carbon tetrachloride and HCl. And we are proposing a three-step mechanism. Step one is a equilibrium step. The dissociation of Cl2 into its chlorine atoms. Step 3 is the reaction of the trichloromethane with chlorine to form this CCl3 thing and HCl. And that has a rate constant K2. Step 3 is the reaction of the CCl3 with a chlorine atom to form CCl4. And that one's going to have a rate constant K3. The supposition is that step 1 is fast, step 2 is slow, and step 3 is also fast. So we have two intermediates in this process, the chlorine atoms and the CCl3. If you were to invoke the rate determining step, you would have the problem of the chlorine being an intermediate in your rate constant. If you were to work through this and use the equilibrium step above, you can express the chlorine and atom concentrations in terms of these rate constants and the Cl2 concentration. I will leave this exercise to you. If you can do it, you will do fine on the exam. And the answer is this. The rate overall is going to be equal to, K2 divided by these times the square root of K1 divided by K negative 1 times chlorine to the 1/2 power and CH2Cl to the first power. So a couple of things I want to point out about this. Non-integer exponents in a rate law actually are allowed. You don't see them that often, but they do come up. And then this whole thing, we could also express, don't forget, this would be equal to K observed. Right. And, well, let's just go ahead and do it since we have time. So how does that work? So you've got K1 times the concentration of Cl2 equals K negative 1 times the concentration of Cl squared. So you want to solve for the concentration of the chlorine atom. The chlorine atoms are the problematic species. So Cl2 squared is going to be equal to K1 Cl2 over K negative 1, which means that the concentration of chlorine atoms are going to be equal to the square root of K1 K negative 1 times the square root of the chlorine atom the chlorine molecule concentration, which I'm just going to do as to the 1/2 power, and then that is where all of that comes from. All right, chapter 13 down, or 14.